I am Eli Perkins. I'm at Eli Perkins most places on the internet, except for on Twitter. This guy is at Eli Perkins, so on Twitter I'm _ Eli Perkins. I work at a place called Clubhouse. We make project management software for making developers' lives easier. There I make React run on phones natively, which is a really fun problem. So I'm here to talk to you about why I love static typing and why it matters. So let's start by talking a little bit about what static typing really means. In static typing, types are known at compile time. These types are constrained throughout the program. These constraints can help us infer what types work where in our program. Some examples of this are Java, or Swift, or Haskell. Dynamically typed programs do type checking at runtime, meaning their values have their types associated only once the program is running. Some examples of this are Python, Ruby, or JavaScript. Types are often determined in statically typed systems via annotation and inference. A developer can explicitly state what type some expression has within the system, or the system can infer the type of some expression based on the constraints that are applied to it. So how do I do this in my JavaScript? If you just said that JavaScript is a dynamically typed language, why are we talking about static types? So there's two major tools that are out there in the world today to apply static typing to JavaScript. Those two big tools are Flow and TypeScript. Flow is a tool based on OCaml and developed by Facebook, and it allows us to annotate our types within JavaScript. Flow can then type check our system for us. This doesn't affect the runtime at all in our application, and it's only a tool to check the types throughout our system before our application begins running. Another is TypeScript. So TypeScript is a language developed by Microsoft, and it's actually a full language that compiles down to JavaScript. And it's a superset of JavaScript. It has some more features to it to allow us to annotate and infer our types. While these two type systems are a bit competing for share in the community, both offer pretty similar functionality in the end. The syntax can begin to differ a little bit between the two, but they offer a similar set of abstractions for applying static types to our system. The examples in this presentation will be focused on Flow, but most, if not all, things that we're going to talk about today in this presentation can be done in both languages. So here's an example. We're creating a new variable x that is of type number with a value of 0. We've annotated the variable with a type in this example, explicitly stating that x is of type number. But we can glean a little bit more info from our knowledge of math here. We know that 0 is a number, and 0 is always going to be a number. So we can drop the explicit type here and infer that variable x is of type number. We know that because 0 is a literal value of type number. We can also annotate functions and their inputs and outputs. Here we say that sum is a function that takes in a number x and a number y. We can infer that the plus operator, when used with a number on the left-hand side and a number on the right-hand side, returns a number. So we know in this example that foo is also of type number. A really cool thing about statically typed systems is that these types become constraints that flow through our system. Here we can apply 3 functions: square, multiply, and sum. And since each of these functions always returns our numbers, we know that x in the end, in this example, will always be a number. We can flow our types all the way through our system in this way. There are also types that compose together. Here's an example of an array that contains values of type number. Here we have 2 different types at play. We have the array type and the number type. Here's another example of composing types using nullability. We could say that the variable greeting in this case is of nullable type string. And it could be either a string or a null value. And we know that because the question mark here annotates this type, saying it could be nullable. This is extremely beneficial when we go to make a system that passes around nullable values. We can define functions that only allow non-null values through and throw errors before our program begins to run when we attempt to pass in a possible nullable value. In this example, the function greet only takes in non-null string values, and thus throws an error when we try to use a nullable string value here. We can write more complex systems that have more types that pass through our system, and we'll always have the type checker looking out for us. In this example, we're trying to access a property on another object that has been annotated as a nullable property. And this is a really easy bug to write because send email could not check for null values inside of the body of the function. But in this case, we have our type checker looking out for us, and we can simply handle the error by wrapping it in a check before we start to run this function. And this helps us eliminate a whole class of bugs. We no longer need to sprinkle in type checks throughout our system to ensure that we're writing correct code. We can reduce the number of bugs that are written. Type systems also allow you to help you know what code to write. We can infer what methods exist on an object or within a scope, and have things like autocomplete help us out, right in our IDEs or our editors. Type checkers could even check for things like typos. If we accidentally slide a few extra letters in there, we don't have to worry about an error occurring at runtime. The type checker can check it before our program begins to run. Instead of having to dive through the debugger and figure out what was undefined as we went through the system, we can have our type checker throw the error before we start running. And type systems also help us express our intentions as well. Here is an example of some React that is using some type checking. We want to create a user component that takes in props of ID and name and email, and we want to ensure that those are always passed whenever we create one of these elements. So in this example, we don't pass the prop email, and as such, we get an error before our system starts running. If you're already using prop types today, you might already be declaring these types in your code. But you're not going to get those errors until you start running your program. This will catch those errors before our program even begins running. A really cool thing about type systems is that you can start to build them up and create better expressions of what you want your code to do. Here's an example of Nuclide, which is an IDE package around Atom, where they've declared a autocomplete function that gets the autocompletes for a certain point in the buffer. And this is really interesting because we see some different types being mixed into our system, not just our base types. Another example of this is AtlasKit from Atlassian. They've created a very large package of all of their UI elements that are all type checked using Flow's prop types. Okay, cool, but my JavaScript works just fine, Eli. Why do I care? Why would I throw types all over my code if it doesn't affect my runtime? Bugs are surprises in our code. No one ever expects to write a bug or does so intentionally. Static types reduce surprises. The type system can give us hints about the types in our code and throw errors before our code is run. And as such, static types reduce the number of bugs that are written. Errors at runtime aren't great. Errors at runtime means that our users are getting undefined behavior. Errors at compile time are much better, on the other hand. That means you, as the developer, are the one paying the cost of preventing these errors. Pushing the errors to compile time mean that we have less undefined behavior in the hands of our users. Static type systems can help developers see and fix these errors that would normally happen at runtime for our users. By showing the weak spots in our code, we know how to properly handle these types. So before I dove into React and React Native, I spent a long time writing Objective-C. Objective-C is Apple's bread and butter programming language that they've been working on and with for a very long time, gaining its popularity back in the days of Next, powering millions of iPhones, Macs, watches, and who knows what else out in the world today. For a long time, I wrote a lot of Objective-C at Venmo. The Venmo app had been written and rewritten, and feature after feature bolted on or mixed in with Objective-C. And that's great because Objective-C just works, and everything was just working. Objective-C is a dynamic language, so you can do kind of scary things like this. We can create an empty array and try to access the 100th item in that array, and boom, our user gets a crash. You can try to make a variable x with the number 1, and try to make it call a function that doesn't exist on the class NSNumber, and boom, our users get another crash. Or take in this example where we're trying to create a networking client to fetch us an array of objects from the server to show some UI to the users. We just have this opaque type array that doesn't tell us more about what's inside of the array. What is the type here inside of the array? Are there even objects in the array? Is there even an array? We don't really know because of the dynamic language that we're working with here. And errors at runtime in Objective-C apps are pretty bad. Errors at runtime mean crashes at runtime for our users. And that meant our users are unhappy, leaving 1-star reviews. That meant our managers and teammates are unhappy because our users were unhappy. And that all made me really unhappy and sad because the bugs were even shipped in the first place. But around the time I was at Venmo, Apple did this really cool thing and made this brand new language called Swift. Swift was a strong static typed language that you could write your apps in. And a really cool thing about Swift was its interoperability with Objective-C, so you could kind of mix and match the two together and just adopt Swift where you needed to. You could write a networking client and have it return values that you told the compiler at the time. So in this example, now we actually see what is inside of our array. We see that we have events inside of our array. And when you try to access things in the array, the language gives us optionals that we are forced to check. The compiler wouldn't even build your app unless you handled all of these types correctly. If you didn't explicitly handle your null types, your app wouldn't build in the first place. And this ensured more correct code. As an app that relied heavily on communicating with the server to make our users happy, networking and how we did network requests was a big part of the app at Venmo. We found that how we communicated with the server and how those communications were read or persisted to the disk was a big source of errors for us. We had a very high crash rate in our core data stack, how we persisted our objects. We replaced pieces of this stack incrementally with more static types. We created a statically typed networking client, statically typed network requests, responses, parameters to those requests, and it created a layer of safety between our networking and persistence layer. One interesting side effect is that we started to see that these static types bled out a little bit more throughout our app. Next thing you know, our view controllers and our views were being statically typed. We had different controllers throughout our app that, for things like managing state that were becoming statically typed. And another interesting correlation that we began to see was the more Swift we introduced the app, the further we saw our crash rate drop. The more static types we introduced, the less users had a bad time. We went from having a number of bugs that were surprising and some undefined behavior in our app to having users that started loving using the app. And they stopped leaving their 1-star reviews, and our managers and teammates became happier because of those nice reviews. And the happier I was for making a computer solve those bugs for me by telling the compiler what the types were to surface those bugs within the type system. And it was just a lot of fun to write this type of code. It became a selling point for our team to write safer code using static types. The more components that we had in Swift, we had more statistical proof about writing safer code. The bugs in our code were surprises, and we never meant to write them. They can get written into code that we inherited, or we could write them ourselves. But static types reduce surprises, and we can create guarantees about our types at runtime. Static types can improve user experience by reducing crash rate. Okay, Eli, seriously, this is a JavaScript conference. Why are you talking about Swift and Objective-C? But the analogy between Objective-C and Swift can be compared directly to JavaScript and Flow and TypeScript. By introducing a static type system, you can help reduce your error rate within your system and stop shipping errors to your users. So I want to shift gears a little bit at this point. I think I've given you a few examples about why static types are nice, but let's talk about what's new in ES 2030 coming up in a few years. Let's just take a look at what's next for static typing in the JavaScript world. So let's start by taking a look at Elm. Elm is a fantastic language targeted at the browser, aiming to make use of types in some really beautiful ways. Taking inspiration from Haskell, Elm generates JavaScript with great performance and no runtime exceptions. No Red Ink is a company who has been using Elm in production for quite some time. Even with all of the Elm that they've deployed to their customers, they still have not produced a single runtime exception in all of the Elm code that they've pushed to production. Yo, like, what? That's insane. Like, no runtime errors? Like, a world where your production code just never threw exceptions? Like, you could just take your phone and throw it away because you'd never get another after-hours Slack message or PagerDuty alert? That's an incredible guarantee. So let's take a look at what Elm looks like and how this wizardry kind of works. Here's a simple increment function that takes an int in and adds 1 to it and returns an int. We've annotated our code here by creating a function that takes in an int and passes out an int. If we were to pass in a string here, it'll yell at you real quick because string isn't an int. And the Elm errors are awesome. They teach you more about the language and what the compiler is expecting to take in and output as well. So in this case, it tells us that we are expecting an int, but we got a string. And this is happening at compile time. Another awesome feature of Elm are unions. Here we've defined a type called primary, and its values can be either red or green or blue. Nothing else. Those are the only values that primary could ever have. If we tried to use write a function that takes in primary, we could switch over it. And in one case, we could say when we get a value of red, let's return a string of red. A value of green, return a string of green. A value of blue, return false. That seems like it might cause some unexpected behavior. We might write a function that expects to get a string back all the time. A really cool thing here is that Elm will catch this for us. It will tell us explicitly what is different here. So here's the error that would be passed out if we were to try to write a function like this. Elm won't even compile it because we've returned 2 different types from this function. If you were to try to compare 2 lists, a list of strings with a list of bools, it will even tell you that those 2 things cannot be compared with each other. Elm's errors are so human, it uses the first person in its error messages to help you teach the language. I mean, like, that's pretty cool, right? That's pretty sweet. So another cool thing about Elm that it does, it's very interesting how Elm manages packages. Humans don't even manage version numbers in Elm. It's all done automatically by comparing the differences in the 2 types between the last version and the current version. If the type signatures of your API are both identical, you get a new patch version. If you've added a new type signature but removed no existing ones, new minor version. If you break, change, or remove a type signature of an API, Elm will give you a new major version. All of this is done by the computer. Humans don't even need to interact with it to create these new version numbers. I mean, like, this is really the power of types here. We can guarantee better experience by our users with types. So that's just a few of the ways that Elm is an amazing language. I would love to talk more about it. You can use Elm today, and I think you'll really love working with it. So next, let's talk about OCaml. Oh, wait, sorry, I meant let's talk about ReasonML. ReasonML is a new syntax and toolchain for OCaml that compiles down to JavaScript. Facebook is pushing forward this approachable cousin to OCaml, trying to bring over some familiar paradigms from JavaScript and make it more approachable. It's only a new syntax and toolchain for OCaml. OCaml's compiler is extensible enough that we can make it output JavaScript. They're building on the sound foundation that OCaml has laid down for the last 20 years. Reason lets us focus on letting developers write code that doesn't make you jump through hoops to handle everyday use cases. Focusing on super quick build times and a safe runtime, Reason leverages the OCaml type system and standard library to write quality code. The JavaScript generated by Reason is so readable that Facebook is actually checking in their generated JavaScript code from Reason. So here's an example of Reason's union type, not too dissimilar from what we saw in the Elm union example. In this case, we have a variant school person. It can have the values of either teacher, director, or student with a name annotated with a string. So notice how we now have this student that can bring a string along with it. We can write a switch over this type. And in this function, we take in some stranger and return a greeting as a string. Notice here that we didn't annotate the type of this function, yet we can already start to switch over the exact types that are inside of it. When we get a student, we can unwrap that string, any other name, and put it in there for us. So if we were to pass in a student named Eli, we would get a greeting for Eli. And the type system recognizes the symbols that we're switching over, giving us the type inference without it needing to annotate it. If we pass in a teacher, we get, hey, professor. But let's flex the muscles of reason a little bit and use some pattern matching to catch all students named Richard. Let's ask them why they're still hanging around school. We can pattern match on the value of Richard for all students passed into this function and treat that case specially by returning a different value. Pattern matching has some really unique use cases that we can start to use here. Perhaps we want to switch over the status code in our network requests, or maybe we want to switch over the network request as a whole and pluck out just the specific static codes. Maybe we omitted a case and we forgot to handle how to greet all students. Reason gives us sane errors that help us catch all of those values. It knows that we didn't handle all of the possible cases of school persons that could be put into this function. And so it forces us to handle it and write more correct code. Reason can catch this before compiling down to JavaScript and give us a safer runtime. The docs call this the crown jewel of reason data structures. There's some extremely powerful things you can express with variants and unions to ensure that you're handling all of the right cases. This is the power of static types at work. The Messenger.com team at Facebook has converted Messenger.com over to Reason about 50% of their code. They're really pushing Reason forward on their product. And their statement about quality code is no joke either. With half of the code on Messenger.com now written in Reason, they've only encountered 10 bugs surfaced because of the components written in Reason. Talk about safety at scale. This is pretty incredible. So that's ReasonML, and just another tool that we can look forward to using in the future with JavaScript. So to recap a little bit, bugs are surprises. We don't ever expect to have bugs in our code. And static types reduce those surprises because we can make the compiler or the type checker point out where in the code we need to explicitly handle things. And as such, static type systems reduce bugs by helping the developers write better code and ensure better runtime safety. So I hope I've shown you a few ways that studying static typing can help you reduce bugs, improve developer productivity, and ship a better product to your customers. Here are some of the resources of the tools that I talked about today. I would definitely recommend going and checking out Dan Grossman's programming language course on Coursera and dive into SML and the power of pattern matching. Brandon Williams is another person who taught me some really brilliant things in Swift, forcing the compiler to write mathematical proofs and prove mathematical code, or math with code. And so that's all I have to talk to you guys about today. I want to say thank you. Feel free to come say hi and talk to me if you have any questions. Thank you.
That was great. Thank you so much.
Thank you, sir.
Now, just a question for you really quickly. Do you find that when things get really static that you have a lot of lint?
I actually have a lint roller at work just for when that lint does come out.
Yeah, because it seems really counterintuitive because I have to use a linter because I'm using a dynamic language, but
yeah.
What's your favorite like hot trick for statically analyzing? Like, what's your favorite like meta thing you can do with static analysis?
Yeah, I think one interesting thing is when you have a static type checker as part of your code, you could be checking your types all of the time. Reason has a really cool IDE setup now where they actually tell you the type inside of a function that you're working in. So like along your Vim tag bar, you can say, what is the input and output of a certain function? You can start to like walk in and out of a function and see that change along the bottom to help kind of just give you that sense of what is the code that I'm writing in this function right here.
Okay, and then last one, this is just a quick yay or nay. Optional static types in the ECMAScript specification, yay or nay?
I'm probably right now, if that was today, I'd probably a nay. I think there's something to be said about dynamic.
So you are horse JS. Yeah.